Here is Franklin Robinson, who's an engineer and technologist in the thermal engineering branch at the NASA Goddard Space Flight Center. He is the principal investigator for a multi-year effort focused on the development of an embedded cooling system for nascent electronic systems, which was demonstrated during 2 recent flights aboard the Blue Origin New Shepard space vehicle. Robinson has supported several technology demonstration efforts throughout his career, including those tested aboard the International Space Station and variable gravity aircraft. He also supports a number of flight projects as manager of the Thermal Technology Development Facility at Goddard Space Flight Center.
All right. Thank you very much for the introduction. Can you hear me okay?
We can hear you well.
Great. All right. Well, thank you so much for the introduction and good afternoon, everyone. And welcome to my presentation on flow boiling in microgap coolers, recent suborbital flight results. My name is Frank Robinson, and the co-author of this presentation is Dr. Avi Bar-Cohen from the University of Maryland. All right, so we'll start with the motivation for this work. Over many years, we've observed trends of increasing power density in many electronic devices, such as integrated circuits, lasers, and power devices. This is especially true for wide bandgap semiconductor devices. We need innovative solutions to cool these power-dense devices. And along those lines, we know that two-phase cooling systems provide high flux heat removal, low pumping power, and little temperature drop between the heat generating devices and the condenser. This is especially important in space applications because of the T⁴ relationship for radiation heat transfer. We also know that pumped loops offer longer transport distances and precise flow rate control, features that are not always available in passive devices. We also see these kind of needs and motivation reflected in the NASA thermal technology roadmaps, which have areas for high flux heat acquisition at constant temperature, micro and nanoscale heat transfer surfaces, and two-phase pumped loop systems. Continuing along the lines of our motivation, we know that some two-phase systems are prone to gravity effects. As shown in the top right image of the slide, we can see that in pool boiling, that it works really well in 1G because we have that buoyancy force to remove generated vapor from the heated surface, but in weightlessness of space, with the absence of that buoyancy leads to a large vapor bubble that actually inhibits heat transfer and can lead to device burnout. So our goal is to develop versatile coolers that work reliably in all orientations during ground testing, low G and high G. Along the lines of what I was discussing earlier in terms of needing higher heat flux cooling, we look at things like embedded cooling. And embedded cooling really is a system where you have direct contact between the heat generating device and the coolant flow. In this case, a dielectric coolant that doesn't conduct electricity, so it doesn't pose any harm to the heat generating device. These devices provide a balance of performance and simplicity because you don't have to modify the chip surface itself, which can be a concern for some of the electronics developers. So we started to look at, embedded microgap coolers, and we thought, oh, wow, well, they're going to be small and compact, so we can probably eliminate some of these G effects that we see in other systems. But we found that there weren't a lot of criteria for orientation and gravity independent performance. And that's something that's kind of the starting point for this work. We wanted to come up with those criteria and make sure that our systems would provide that great heat transfer we needed, but also eliminate any risk due to operation in different orientations or different gravity environments. So the approach we've taken with this technology is to start with ground-based testing to characterize the parameters that govern the thermofluid behavior, and then proceed to suborbital flights to establish the effects of low and high G environments. And that's going to be the focus of today's presentation. Ultimately, with any technology development project at NASA, we really want to integrate our technology with flight projects to complete the technology maturation process. And some of those flight projects might include lasers, 3D integrated circuits, or deep space missions. But like I said, today we're going to focus on the suborbital flight experiment, and the way that we obtained those results was by flying a payload on the Blue Origin New Shepard space vehicle, which is a suborbital reusable space vehicle that takes off and lands vertically, has about 100-kilometer apogee, and provides about 150 seconds of weightlessness. In our case, our payload was housed in what's called a single payload locker, which is about 520 by 410 by 240 cubic millimeters. That's roughly the size of a carry-on bag for most commercial airliners. The payload was limited to about 11 kilograms, and the interface to the flight vehicle is done through what's called an integrated payload controller, and that provides power, and it also provides some other sensors, analog inputs, analog outputs, digital inputs, and digital outputs. They've tried to make that interface as robust as possible to cater to as many customers as possible. In this specific flight, the heart of the experiment is what we call the microgap cooler, and the heart of that device is really the test chip. And the test chip in this case is a 12.7 by 12.7 by 0.6 cubic millimeter thermal test chip. So pretty compact, small test chip, low weight, low mass, and it's silicon. There's no surface enhancement on the silicon. It's bare polished silicon. The channel itself is 0.17 millimeters tall, 13 millimeters wide, and 12.7 millimeters long. And in this case, we're looking at flow boiling of HFE 7100, which is a non-toxic, low vapor pressure dielectric coolant. We are limited in the number of parameters that we can change per flight. So, we really kind of set everything. And in that way, we only change the gravity level through the flight. That's the goal. And so our heat flux is about 140 kilowatts per square meter. Our mass flux is pretty low at about 500 kilograms per meter squared second. And we're looking at a saturation temperature of about 50 degrees C. It's worth noting that we can achieve much higher heat fluxes with this setup. We've been able to show that on the ground. But in terms of gravity effects, we found that higher heat fluxes obviously lead to higher vapor generation, and that increases the average velocity. So that is actually a less conservative case to test for G effects. And that's purposely why we kept the heat flux a little bit lower in this situation. Right. Now we'll get a little bit more into the payload itself. This is our base plate. It's about 18 inches wide and 14 inches tall. We have an array of filters and DC-DC converters right on the base plate. We have a payload data system that provides closed loop temperature control for various heaters in our system. We have an onboard accelerometer and a camera that was provided by Blue Origin. The next layer of the payload is the actual flow loop itself. And so we have a two-phase reservoir that lets us control the saturation temperature and pressure, gear pump, a turbine flow sensor to measure the volumetric flow rate, a preheater to get the liquid temperature cooler, the microgap cooler itself. We have two pressure transducers to measure the pressure at the inlet and outlet of the microgap cooler, and a condenser that it relies on a paraffin wax phase change material to provide a constant sink temperature throughout the flight. Everything assembled, this is what the payload looks when it's assembled and housed inside of the. Addition here is that at the top you can see some connectors that's the integrated payload controller. So that's kind of the primary interface between the payload and the flight vehicle. All right, so next we'll talk about the flight itself. Take you through the entire flight sequence. So here, this image is Blue Origin New Shepard vehicle on the pad, ready to take off. Early morning at Blue Origin's West Texas launch site. Here's Blue Origin New Shepard right after liftoff. You can see one of my favorite things about this picture is that you actually look through the window on the crew capsule, which is at the top of the vehicle, and actually see our payload locker. I like like to joke that we paid extra for this highlight, but it's purely accidental.
Yes, we can see the screen.
All right, well, I apologize for the technical glitch there, and I'll speed up a little bit to get things moving along. So we were just talking about how the vehicle takes off, and then, the vertical landing aspect of the vehicle is when the propulsion module comes back down and lands on the landing pad, which is only a couple of miles away from the launch pad. And here you can see what the propulsion module looks like after it's landed. Notably, the crew capsule is missing. And here's the crew capsule coming down separately. There are a series of drogue parachutes to slow it down, and then some main parachutes that take it all the way through the ground. And then here's the crew capsule on the ground, and you can see that the Blue Origin team members are servicing the vehicle before they bring it back to the vehicle processing facility. So now, in terms of the flight profiles that we got on the two flights, you can see on the left here the altitude, and in both cases, the apogee was more than 100 kilometers, which is about what we're expecting. It's about 10 times as high as a standard commercial airplane will fly. And then on the right, you can see the acceleration magnitude that we saw. During the ascent, the acceleration peaks at about 3 Gs. Then there's this 150 seconds of weightlessness, followed by a high G descent, and then various perturbations as the parachutes deploy and the vehicle lands. Now for the heart of the presentation and the experiment, what we're looking for is this is the payload. And so basically 300 seconds before liftoff, we have a rapid increase in the reservoir temperature. That's, by default, that's our control. When we reach the desired saturation temperature and pressure, we activate the pump, preheater, and thermal test chip in quick succession. And actually, we start, the preheater in this case reached its set point during the microgravity coast. So there are 5 vertical lines. The first one is liftoff, and the second one is the start of the microgravity coast. So we were a little bit off in this case in terms of when the preheater hit its steady state temperature. We were hoping that would be prior to the microgravity coast. After touchdown, which is the last vertical line here, we have a shutdown sequence that is initiated. In terms of the heart of the experiment, the micrograv cooler and the thermal test chip, here are the temperatures that we observed. See a rapid increase in the thermal test chip heater temperatures right after it was enabled. This is single phase liquid cooling, and across the chip, even though it's very compact, we see a 21 degrees C gradient. After the onset of nucleate boiling, the gradient is dramatically decreased down to about 4 degrees C, and the absolute temperatures are reduced dramatically as well, from more than 100 degrees C to about 70 degrees C. Throughout the various phases here, you can see minor fluctuations through the microgravity coast, the high G descent, and landing, but we think that those fluctuations are linked to the preheater, and I'll explain why we think that is in the next slide, or excuse me, in 2 slides. Here we have the heat transfer coefficients. This gives us kind of greater fidelity into the local temperatures and across the chip. Much better sensitivity than the temperatures alone. And what we see is initially, right after power on, we do see a variation in the heat transfer coefficients, and that's due to developing laminar single phase liquid flow across the chip. And then we have the onset of boiling, which actually starts before we take off, before lift off in the vehicle, and proceeds all the way through the flight profile until 2 minutes after touchdown. You see some kind of oscillations and perturbations during the microgravity coast phase and throughout the rest of the flight, but we think that those are really linked to the preheater behavior and the reservoir behavior. The saturation temperature and pressure oscillate a little bit, and the preheater actually injects a little bit of vapor into the inlet manifold, which disrupts the flow. But we didn't see any clear trends with gravity, which is what we were looking for. Probably one of the more notable things on this chart is near the 4th vertical line, which is right at the end of the high G descent. There is kind of a noticeable and real drop in the heat transfer coefficient. And this next slide here explains that a little bit. During the microgravity coast phase, we started to see vapor being injected to the evaporator inlet. That was from the preheater. During the high G descent, this behavior briefly goes away, and we think what happened was basically there's flow into the evaporator, but some of the liquid flow is actually going to collapse vapor rather than flowing through the test chip. So this is a reduced flow through the microgap, which would cause concern that would, suddenly the flow rate is reduced, so the heat transfer is not quite as good. And we were able to back out and backtrack that the preheater vapor generation is explained by the Richardson number, which is not something that we had accounted for. When we test in the when we test in the lab, we're always in a 1G environment. And so we didn't see this vapor generation at all. But in microgravity, or the weightlessness that we experienced during flight, we think the convective heat transfer at the preheater diminished to the point that we actually started to generate vapor. And in the future flights, we're going to add a temperature sensor there so that we can kind of better understand what's going on with the preheater. Now I'll talk a little bit about hydrodynamic regime maps. These were first introduced by Reynolds, Sod, and Soderly way back in 1964. There's been some recent interest. And these maps, what they do is they separate two-phase flows based on whether they'll be dominated by surface tension, inertia, gravity. Dominant regimes, and there are boundaries among the regimes. We've found through our ground testing that these maps have worked quite well in predicting orientation effects for our microgap cooler. And that's when we operate the evaporator in different orientations relative to Earth's gravity. We also looked at using these maps for the flight data, and you can see there on the right, P7 and P8, and how our bond number varies throughout the flight. And that's purely because the bond number is a function of the gravity level. And so you can see that we're pretty firmly in that inertia-dominated regime, which means we shouldn't see a lot of gravity effects in the microgap cooler itself. For future flights, what we'd like to do is use larger channels, which will increase the bond number, lower flow velocities, which will reduce the Weber number. And the combined effect of that is that we'll get much closer to that boundary between the gravity and inertia-dominated regimes. So right now, we think the microgap cooler is firmly in the inertia-dominated regime, but we're not confident, or we're not absolutely sure where the boundary between inertia and gravity-dominated behavior lies. And so with future flights, if we approach that boundary, we should be able to resolve it with greater fidelity. And as I already alluded to in terms of the future work, we do have an upcoming flight on New Shepard that will implement that larger channel height and the lower mass flux. We've also added a second accelerometer to give us better fidelity into the triaxial acceleration. We are going to be monitoring the preheater temperature to give us a better sense for that vapor generation at the preheater outlet. We'll also be measuring them correctly, which should give us a better fidelity on the flow rate. Ideally, we'll have some follow-on flights that would even further let us resolve that boundary, but those are, of course, not guaranteed. And then we will rely on any ground-based orientation tests to fill gaps in the data. So now I'll wrap up with a summary and conclusions. We studied the effect of gravitational acceleration on flow boiling of near-saturated HFE 7100 in a 0.17 millimeter tall by 13 millimeter wide microgap. We found that flow boiling provided the high heat transfer coefficients and low temperature gradients we were looking for. And despite the modest mass flux, gravitational acceleration had little effect on the thermofluid behavior in the microgap cooler. However, the variation in G did have effects in other parts of the system. We also found that the hydrodynamic force regime maps, based on formulations of the non-dimensional numbers developed during the ground test, successfully predicted the behavior we observed. We hope that future flights and additional ground testing will broaden our data set and further improve our predictive capabilities. With that, I'd like to acknowledge funding from the NASA Center Innovation Fund, NASA Flight Opportunities Program, the Thermal Technology Development Facility at Goddard Space Flight Center, with a special acknowledgement to Colton Colhill and Michael Chapman, who were instrumental in developing the payload. I'd also like to acknowledge the Blue Origin and NanoRacks teams. Here are the references used throughout my presentation here, the abbreviations, and then finally, I'd like to thank you very much for your attention and for your patience as I work through that technical issue. If you have any questions, and there's time, I'll be happy to take them now, or you are, of course, welcome to email or call me. Thank you.
Thank you very much, Frank. That was very informative. I think we have time for a question or two. I don't see any in the chat yet, but I also know there's a fairly significant delay, so we'll see if we get any. But we can start with one we've got. Looks like the loop saturation condition is set by the reservoir state through a heater. How is this measured, and how are you able to ensure that the heat is being applied to the liquid vapor interface and not just superheating the vapor?
Very, very good question. Let's see if I have a picture of it. The heaters are covered, but we do have a wick structure that is housed within the reservoir, and based on the charge calculations, I ensure that the wick is always wetted and supplied with fresh liquid, and there by it being a wick, it always has liquid present, and so therefore the heaters being just outside of that wick through the aluminum wall, we were able to ensure really good response there, that we get the temperature we're expecting. We are measuring the vapor temperature. You can see it on top of the reservoir there, and that feedback is what controls the two heaters in the reservoir.
All right, we got a question from the chat. Have you considered the fluid sloshing behavior in microgravity conditions?
Sure, that's another good question. In this case, fortunately with the reservoir, we do, we know at the beginning that we're fully flooding the loop with liquid, and then but that goes away obviously as soon as we start generating vapor, and that is something that we have to track. We do look at we're not just looking at the Z acceleration, we do look at the X and Y accelerations to make sure that any residual rotation or any accelerations in those directions don't have a significant effect on the fluid flow, but it is something that we'd like to better understand because the length scales are much longer in those dimensions. So it is possible that some residual accelerations could have a significant effect.
All right, thank you, Frank. I think that's all the time for questions we have today.